Hi, this is Joey Federico, and I am solving number 46 on page 283 of the Giancoli textbook. The question reads, water at a gauge pressure of 3.8 atm at street level flows into an office building at a speed of 0.6 meters per second through a pipe 5 centimeters in diameter. The pipe tapers down to 2.6 centimeters in diameter by the top floor 18 meters above, where the faucet has been left open. It first asks us to calculate the flow velocity. So in order to do this, we need to use the volumetric rate of flow equation, which is area 1 times velocity 1 is equal to area 2 times velocity 2. So we're given A1, A2, and the original velocity. So all we need to do is solve for V2. Also, to plug these things in, you know that the area of a circle is pi r squared, so the area of the cross-sectional area of this faucet in the first section would be pi times the radius squared. You're given the diameter, so that would be 2.5 centimeters, which is really 0.025 meters squared, times the original velocity, which is 0.6, all over the area of the second part of the tube, or the faucet, which is the diameter is 2.6 centimeters, so the radius would be 0.013 meters. Square that. Now you can obviously cancel out pi, and when you run that through your calculator, you get 2.219 meters per second. And you can use this to solve the next part of the problem. The second part of the problem asks for what the gauge pressure is in a pipe 2.6 centimeters at the top floor, which we know is 18 meters above ground level. In this problem, because we're dealing with kinetic energy and gravitational potential energy, we use Bernoulli's equation, because Bernoulli's equation uses the kinetic energy and gravitational potential energy to derive his own very fluid equation, which is, P1 plus 1/2 rho v squared plus rho gy is equal to a constant. So we know if this whole thing is equal to a constant, then that means that if whatever value of pressure is here, we can find the value of the pressure right here. So using what we know, we can just, we know that if we call this plane right here 0 meters and this plane at the top 18 meters, we can cancel out rho gy 1, and then we can get this long equation. Pressure 2. I just algebraically solved for the pressure at the top of the tube, and just so we can use values that we already know. So the pressure is, in the first part of the pipe, is 3.8 atm, which we have to convert to Newton per meter squared. So that's plus 1/2 rho, which is density, and we're using water, so that's 1,000. Times velocity 1 velocity 1 squared, which we know is 0.6, because that was given to us in the problem, minus 1/2 rho v2 squared. And we figured out that in the last problem, v2 was equal to 2.219. So we just use that and plug it in here. And then subtract rho times g is 9.8, obviously, times y2, which we know from the problem is 18 meters. That equals P2, and when you run that through your calculator, you get 2 Newton meters squared, which runs along the lines of 2 ATM. Thanks.